Clayton Spinner here. Here are my answers for the quizzes. I wasn't able to complete every single answer, but what I'm going to do is just go through everything that I do have. I'm just going to explain each answer to the questions one by one and just go through both quizzes in this video. So first question, it's the simplifying of the MIPS ISA. Basically, this one is taking out offsets, and the way you do that is this way. What you do is, instead of doing an offset, you can split it up into two commands. You add 16 to R2, which contains the address that you want to go to in memory. You store that in R1. Now, the reason you don't store it in R2, say like this, and then do this, is because you want to preserve all the original information that is contained in this original line, which after this load word executes with the offset, you still have the value of R2. So say if you still wanted to use R2, this way would erase that value because you'd be adding 16 to it. You'd lose the original value of R2. So what you do is you want to store it in R1, and then you just simply load word from the address in R1 into R1. This address gets overwritten, but it's okay because that was the original address plus 16 anyway, which was never stored anywhere in the original instruction. So this will work for it. Second question removes register indirect addressing, and that's done by doing this. A little more complicated. Basically, what you have to do is you have to be able to load a word into a register without doing what we did in the first one, using another register to tell it where to go. So the way you do that is you have to create a label and you have to use a third register. The label L1 starts down here. Basically, it just has this command in it, load word R1 0, that's hex to just say 0. And this command is empty, except for it has the load word bit set in at the top of the word. So you just leave that for there. You load that into R1. So now R1 has this command in it. You add, this is where you calculate the offset and the address. You store it in R3. This is the third register that we need. You do a logical shift right to R3, and the reason you do that is because this command here is the load word and the store word. The way he's changed it is it appends 2 zeros onto the end. It does a logical shift left by 2. And these zeros are added because we're only doing word addressing where you can't address to the byte, the individual bytes or the half words. So they stick 2 zeros onto the end of the 16-bit number that we give it. So basically, this step is undoing that because eventually, when we apply it down here, it's gonna shift everything up by 2. So we just prepare for that. So then what we do is we add the address R3, add it to R1, which remember already has load word stored in it in the upper bits. But R3, the address plus 16, is going to be in the lower bits, so it won't actually change this load word. So we've still preserved this command in register 1. Add it, store the new value of R1 at L1, and then when you run this, basically R1 has the offset. It takes in nothing, but it still shifts up the bits by 2, and then you still have this load word in here, and it runs it, and it will pull the address out. Basically, this 0 here is the immediate 16 we give it, but it really doesn't do anything. It just causes the shift up by 2, which makes the address we already put into R3 correct. So this will work for that. Okay, so for question 3, he wants to only use absolute addressing in a subroutine. And basically the way this is done is originally he has a a jump return using register 31. So the way we do that without having that jump return is this is just a portion of the code here, the branch on not equal to R5L1. Once I is equal to B, it will go through here and start executing this code. First you load the address for the return name, for the return label into R5. You add to it the address in R31 that you're going to be returning to, and you store that back in return. So now return has the return label, and then at the end of it, the address for 31 for whatever called this subroutine. Then you just zero out R5, set it back to 0. So basically, jump will execute, and it won't jump to memory spot 00 because we already put the address from R31 into this label at the end. So jump will actually go to the correct spot. We'll go to R31. Okay, question 4 was filling out the table for the return on 0 function, or rather command. Basically, return on 0 instruction provides fast return from a subroutine calling using R2. It checks RS. If it's not 0, it just keeps going as normal. If it is 0, then it loads up the return address from RT and goes to it. It also increments RT by 4. So what we do here is ret0 is the first line. First, it loads up RS into A. This is going to be the check that it does. Z stands for branch on 0. If it's not 0, it will just continue on normally. As you see here, micro branch to fetch 0, and then fetch 0 just grabs the next command as normal. If it is 0, it will jump to retz1. Now the settings here is you want to enable, for the register select, you want to enable RS because that's what you're going to be grabbing. You're not writing to it, but you are loading into A, so you enable that. We're not really doing anything else here, so we don't care about it. Z is what checks for the branch. It's the micro branch. For micro branch to fetch 0, I just put in the commands that the no-op has from this table. I assume they basically acted the same. You don't really do anything. You just kind of jump to fetch. retz1 is where it gets interesting. You load RT into the memory address, or the memory address register, and then you also load it into A. And so you're going to need RT here. So register select it. You're not writing to it, but you got to enable it. You are loading into A again. You are also loading into memory address register. You want to enable memory, or sorry, set enable memory to 0 because you aren't pulling anything from memory yet. And then you just carry on to the next instruction. Once MA is done finding that slot in memory and returning the memory, you're going to put that new memory address into the program counter. So here you need to enable the program counter from register select. It is going to be written to, so that's 1. I disabled load A from before. Disabled MA from before. Turned off memory writing, but enabled memory. So basically, I can pull information from the memory, and I'm going to put it into the program counter. Now, originally, this was written as these two commands were both written as retz2. I split them up, though, because they're each pointing to different... They select different registers. One is the PC and one is RT. And I wasn't sure if you needed to have these as separate commands, or if you could, say, do like that. Select two things at once. I thought you could only do one with the register select, mux. So what I did is I just split them up into 2 commands. This one's RTZ. I now increment RT, which we have to do. So again, RT, it's going to be written to. This time the ALU is doing an operation. This is the operation it does, increment A by 4. So you enable the ALU, turn memory off from before, and then it just continues on. This should actually be N. And then there's the last command, retzz4, microbranch to fetch, basically the same as retzz0, microbranch to fetch. I just make sure everything's off, and I jump back to fetch 0. These two here, I wasn't sure if they needed to be specified as 1 again, or if I could just leave them as asterisks, because they should be 1. We're enabling the register for both PC and RT. But enable register is already set from retzz1. So I didn't know if this was redundant or if you could just do that. But either way, these are going to be set to 1. The enable register is going to be set to 1 for these 2 commands. That's my answer for number 4.